Let's see how this law of diagnosing before you teach works with an example, the concept of feeding relationships. The first step is to identify any concepts that are important for students to understand before you start the new material. In this case, we're teaching food webs, and we're building on the earlier concept of food chains. This is usually taught in primary school. Students are also likely to have knowledge of their own about what eats what from informal learning, and it's important to activate this too. This is an example of a typical approach to checking on prior knowledge taken from a publisher's scheme. Take a minute to read the instructions. From this, we can infer that designers thought it was enough to activate students' recall of the key terms relating to food chains. But there's no active thinking expected, i.e. this implies that only some factual knowledge is sufficient grounds to proceed to food webs. But the third law tells us that what matters more is the understanding students bring with them, the model in their heads. This activity doesn't reveal this, so it's not likely to be helpful to the teacher in deciding if the students are ready to learn a new concept or not. Here is our improved version. It's designed to reveal if students understand what a food chain is by having to make one. This will reveal whether students know how to represent what eats what correctly, use the arrows correctly, which is a common problem, and gives an opportunity to show that the arrows represent the flow of energy from producers to prey to predators. Now imagine that you're teaching the physics concept of weight. Gravity is something students clearly have accumulated a lot of knowledge about in everyday life. As this could either help or hinder the teaching of weight, we need to probe what it is that they understand. So what we've done is to concoct two situations that will expose whether their ideas are consistent with what we're about to teach, or whether they might be obstacles to understanding how gravity works. In the first case, students may believe that gravity always acts in a fixed direction, downwards, rather than it being a force of attraction towards the centre of the Earth. This might lead them to draw all of the yo-yos going down the page. The second case probes more deeply into the notion of gravity. Students might believe that motion is the result of a single force, and so might reason that if objects fall down slopes, gravity must also be acting along the slope. You'll probably be wondering what to do if the diagnostic assessment shows that many students have got a significant knowledge gap or a misconception. This is where we move to the second stage of Activate, which we've called Rethink. Rethink is like the doctor prescribing a treatment after diagnosis. In this learning situation, the intervention is designed to help as many students as possible achieve a secure understanding of gravity that can then be built upon. Rethink is about getting students to question their existing ideas. They don't need to be labelled as misconceptions. Scientists regularly improve their ideas and throw out old ones in the light of new evidence. So why not model this by saying, OK, let's see if that idea works. Then give students a new situation to test it in, i.e., what would happen if you turned the globe upside down, and then the person at the bottom would be at the top? What would you expect to happen to the yo-yo now? Let the students think through why their idea might be wrong for themselves. This is as important as presenting the correct scientific view. The other challenge is what to do with students who've shown they understand the prior concept. This is where extend activities come in. They could be given some more challenging situations to puzzle out in groups. This would keep them engaged and also provoke questions that the concept they are about to learn about will answer.